All right, hello everyone, and welcome to the first lesson of Unit 7 for AP Chemistry, which is on Introduction to Equilibrium. Today, you should understand that some reactions can occur in both forward and reverse directions, sometimes proceeding in each direction simultaneously. You should be able to explain the relationship between the occurrence of a reversible chemical or physical process and the establishment of an equilibrium. Our essential knowledge includes many observable processes that are reversible and can experience equilibrium, like the evaporation and condensation of water. And also the understanding that when equilibrium is reached, no observable changes occur in the system, and your reactants and products are simultaneously present. We also go over what a dynamic equilibrium is and how to graph equilibrium. So chemical equilibrium is defined as the point at which the rate of the forward reaction equals the rate of the reverse reaction. So early in a reaction, the forward rate is going to be high because reactant concentrations are the greatest, and your reverse rate is going to be initially low because we have few products that are present. As those products form, the forward rate is going to decrease and the reverse rate is going to increase due to more frequent effective collisions involving your products. Eventually, these rates become equal, establishing a dynamic equilibrium. At this point, concentrations remain constant even though reactions continue at the particle level. Now, in Unit 5, we learned that reaction rates depend on factors like concentration, temperature, and collision frequency, and that rates typically change as a reaction proceeds because reactant concentrations decrease while product concentrations increase. That perspective is going to directly explain how equilibrium is established. So, as a reaction progresses, the forward rate slows because there are fewer reactant collisions, while the reverse rate increases as more products form and begin colliding to reform reactants. So equilibrium is reached when those two rates become equal, meaning the rate of the product formation equals the rate of the reactant formation, which is shown there in the equation. Chemical reactions can be classified as non-reversible or reversible based on whether products can reform into reactants. In non-reversible reactions, reactants are going to be converted into products, and the reverse process is essentially negligible under those conditions, meaning the reaction essentially just proceeds in that one direction. Now, in contrast to that, when we deal with reversible reactions, that's going to have a reaction that allows both forward and reverse processes, and they are able to occur simultaneously, which makes equilibrium possible. Many common physical and chemical processes are reversible, including phase changes like evaporation and condensation, dissolution and precipitation of ionic compounds, acid-base proton transfers, and redox electron transfers. And being able to recognize whether a reaction is reversible is really important because only reversible reactions can establish dynamic equilibrium. And the easiest way to identify whether a reaction can partake in dynamic equilibrium is the double-headed arrow. So in chemical equations, the type of arrow used communicates really important information about the reaction. So the ones we've been using so far are the single-headed arrows. Those are often treated as irreversible reactions. So you can only go in one direction. But today we are going to be working with the double-headed arrow, and that's going to tell us that we can establish equilibrium. So dynamic equilibrium is going to describe a state where the forward and the reverse reactions are occurring simultaneously at equal rates, meaning the reaction has not stopped. However, there is no net change in concentrations. So when we have dynamic equilibrium, the reactant particles are still forming products and the products are still reforming into reactants, but those opposing processes are going to balance each other out. It's important to note that when we're talking about a dynamic equilibrium, it has to occur in a closed system where the reactants and the products are going to remain present throughout the entire reaction. And although concentrations stay constant at equilibrium, it's really important that you realize that particle motion and reactions are still going to go on during that equilibrium. A great way to imagine this is using the image provided on the right here. You can see that motion is occurring even though we don't have an overall change. So the girl is staying in the exact same spot. However, she's moving up and the escalator is moving down. And so it's just kind of a kind of way to be able to visualize dynamic equilibrium. A common example of dynamic equilibrium is the phase change between liquid water and water vapor. So let's kind of go through the steps of what's happening at the particle level to understand this dynamic equilibrium. So first you have a closed system and you have a liquid, in this case liquid water. Some of those liquid molecules are going to have enough kinetic energy to escape the surface and enter the gas phase through evaporation. Once you have those vapor molecules, they are now able to collide with each other and the liquid. And when they collide with the liquid, they can return back into liquid molecules through condensation. As you move forward in the reaction and your vapor accumulates, the rate of the condensation is going to increase until it equals the rate of the evaporation, which will then establish your dynamic equilibrium. So at that point, the vapor pressure is going to become constant, even though you still have molecules that are continued to move between phases. And just an important note about equilibrium vapor pressure is it's going to depend on temperature and intermolecular forces. It will not change just based off of the volume of the container. So if you were to increase the volume of the container that you see here on the screen, all that's going to do is create more space, and those molecules are then going to have to evaporate, and the whole process starts over again, and you're eventually going to reach the same equilibrium that you were at before in the smaller container. All right, so let's go over how to interpret graphs based off of chemical equilibrium. So there are two types that I want to talk about today. The first one is rate versus time graph. So when we're talking about rate versus time, we know in equilibrium, our forward reaction rate is going to be equal to that of our reverse reaction rate. So when we're looking at graphs that is rate versus time, we're looking for a plateau where our forward reaction is the same as our reverse reaction. So that would be when equilibrium is established. Now for a concentration versus time or a pressure versus time graph, that's going to look a little bit different because it is very rare that we have the perfect amount of reactants and products at equilibrium. So when we're looking at concentration or pressure, typically you're going to have different amounts of reactants versus products. That's okay. You are just looking for when they are held constant, not when they are the same, but when they are constant. So we can see here at this line, our concentration of products and concentration of reactants stop changing or remain constant. So that is where equilibrium exists. All right, this example problem says at approximately what time is equilibrium established? So equilibrium is going to be established at the point where the concentrations of reactants and products stop changing and become constant over time. So on a concentration versus time graph, this is going to correspond where the curve kind of levels off. And in this example, that is going to be at time D. So time D would be the answer for this question. Building on the idea that equilibrium is identified when concentrations become constant over time, it's really important to understand how catalysts influence this process. So if we are to introduce a catalyst, it does not change the equilibrium concentrations of reactants and products, and it also does not shift the equilibrium position at all. So when we introduce a catalyst, all it's going to do is lower the activation energy, for the forward and the reverse reactions, which just increases the rates equally. So when we are introducing a catalyst into an equilibrium reaction, all we're doing is speeding up the process to get it to its end equilibrium point. And that is shown on the graph here. We can see that our end result of reactants versus products is going to be the same with and without the catalyst. It's just the catalyst is going to get us there way faster. Once equilibrium is established, we have to have a way to describe it quantitatively, which is done using equilibrium constants. So equilibrium constant is going to express the ratio of products to reactants at equilibrium and only is going to depend on temperature. So two common forms used in AP chemistry are Kc and Kp. Kc is going to be written using molar concentrations, and that is typically applied to reactions in solutions. Kp is written using partial pressures and is used for gas phase equilibrium. So both constants are going to describe the position of equilibrium rather than how fast the equilibrium is reached, meaning they're going to tell us directly whether a reaction is either reactant favored or product favored, which we will go over in the next lesson. All right, so to actually quantify equilibrium, we write what's called an equilibrium expression based on the balanced chemical equation. So for a general reaction, the equilibrium constant is written as the concentration or pressure of the products divided by the concentration or pressure of the reactants, and each one is going to be raised to the power of its coefficient from the balanced chemical equation. So when we are doing Kc, which is for concentration, remember that you're putting those values in brackets. Brackets is going to indicate that it is molar concentration. And then with our Kp, we're going to use the pressure of whatever we are finding. So for example, if you have C as your product, it will be the pressure of C raised to the coefficient in front of C from the balanced chemical equation. All right, so let's do an example of both getting the expression and plugging in the values to solve for K. So here we have an equilibrium, N2 plus 3H2 reacts to form 2NH3. An equilibrium mixture is given in a 4-liter vessel, and it's asking you for the value of Kc. So first what I want us to do is do just the expression. So the expression plugs in no numbers, it's just rewriting the relationship between the products and the reactants. So if I'm solving for Kc, I'll start with Kc equals, remember when we're doing K, it's always products over reactants. And since we are doing C or concentration, we're going to put these in brackets. So it's going to be the concentration of NH3 raised to the coefficient from the balanced chemical equation, which is 2. And then on the denominator, we're going to have our reactants. So we have N2 raised to the first power, and then we have H2 raised to the third power. So this is what's called our equilibrium expression. And this is quite commonly tested on in AP chemistry, where you have to either write out the expression in an FRQ or identify it in a multiple choice equation. So now from here, we can go ahead and plug in our values to this expression to solve for Kc. Now, this does require a little more work just because we do not have concentration. However, we do have moles and volume, so we can divide those numbers by 4, and that will give us our concentrations. And now that we have those, we can go ahead and plug them into our expression. So Kc is going to be equal to 0.4 raised to the second power divided by N2, which is 0.2, times H2, which is 0.3 raised to the third. And now we can plug that into our calculator and solve for K. So that's going to give us a Kc of 29.63. And looking at our number of sig figs, it looks like we need 3 sig figs from our given information. So we cut off here, so 29.6 is going to be our Kc value. And equilibrium constants are going to be unitless, so there are no units. All right, and let's do a few more equilibrium expressions just because they are important for this lesson. So if we are solving for Kc, remember whenever we're solving for equilibrium constant, it's going to be products over reactants. And since we are working with C or concentration, we need those in brackets. So first our product is I3 minus, and we only have one of those, so it's raised to the power of 1. And then we have I2, which again only has a coefficient of 1, and iodide, which again only has a coefficient of 1. So there we are done with our expression for that one. Now over here, again, it's asking for Kc or concentration. So I'm going to do my products, which is SO3 raised to the second power divided by SO2 raised to the second power times O2 raised to the first power. So those are our Kc expressions. All right, so now let's do an example with Kp. So it says consider the equilibrium at a certain temperature. The partial pressures for each component are as follows. What is the value of Kp? So remember when we're doing Kp or pressure, we are not using brackets because that is for concentration. So we are still doing products over reactants, but it's going to be in parentheses, and it's going to be the pressure of our product, in this case O2, raised to the power of its coefficient, which is 1, and the pressure of NO2 raised to the coefficient of 4. And then on the bottom we have our reactant, which is the pressure of N2O5 raised to the second power. And since we already have our partial pressures, we can go ahead and just solve for Kp. So the partial pressure of O2 is 0.296. The partial pressure for NO2 is 1.7. That's raised to the fourth power. And then our partial pressure for N2O5 is 2. That's raised to the second power. And that gives us a Kp value of 2.09. All right, so let's move on into 7.2, which is on direction of reversible reactions. So today, your objective is to explain the relationship between the direction in which a reversible reaction proceeds and the relative rates of the forward and reverse reactions. At equilibrium, both reactants and products are going to be present, but they're not necessarily present in equal amounts. So the relative amount of each is going to help us determine the position of equilibrium and tell us which side is favored. So when an equilibrium mixture contains more products than reactants, then the reaction is going to be described as product favored. If the mixture contains more reactants than products, then it will be reactant favored. So you can see in these two dynamic equilibrium graphs here with concentration versus time, in the left graph, we have our blue products having a much higher concentration than our reactants, which means at equilibrium, this one will be product favored. However, in our other graph on the right here, we can see that the reactants went down in concentration and the products went up in concentration. However, we still have a higher concentration of reactants, so this one would be reactant favored. All right, so the equilibrium constant is going to help us understand whether a reaction is reactant favored or product favored. And when I'm thinking of K, I like to relate a number line to my balanced chemical equation. So if this is my equilibrium equation, I think of K equals 1 as the arrow. So right in the middle, K equals 1 means I have an equal proportion of my reactants and my products at equilibrium. Now, if I move to the right, I'm increasing K, I'm also increasing my number of products. So if I have a number like 4.1 times 10 to the second, that's going to be bigger than 1, but it's not going to be a huge number. So this means that at equilibrium, I still have reactants and products, I just have slightly more products than reactants. And then if I have a number like 3.8 times 10 to the 34th, this is a huge number. This is going to tell me that at equilibrium, I'm pretty much going to have all products and very few reactant molecules. And then going in the opposite direction, if I have a number less than 1, I'm now going to be increasing my number of reactants. So let's say I have a value like 7.1 times 10 to the negative third. That means at equilibrium, I'm still going to have reactants and products in the mixture. However, I'm going to have more reactants than products. And then same goes for my really, really small number. So if I have something like 1.9 times 10 to the negative 31st, this is a really small number. So it's going to tell me that at equilibrium, I pretty much have all reactants and very few product molecules. All right, so here we have some particle representations of an equilibrium equation. So I'm going to interpret this as water. So we have 2 water molecules in a reversible reaction with O2 and 2 H2s. So now what I want you to do is pause the video and look at each particle diagram and tell me what you think the K value will be. You can either write K is greater than 1, K is less than 1, or K is equal to 1. So when I'm trying to decide my K value for these specific diagrams, I'm going to look at my ratio between water and hydrogen gas molecules because they have the same coefficient. So looking at A, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 water molecules. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 H2 molecules. So if I have 12 waters and 11 H2 molecules, that means I have slightly more reactants than I do products. So my K value is going to be slightly less than 1. Now in box B, I only have 2 water molecules and I have 21 H2 molecules. So this is going to tell me I have way more products than reactants. So my K value is going to be very large. And then for box C, I have 20 water molecules and 2 H2 molecules, which tells me I have way more reactants than products, which means my K value is going to be way less than 1. All right, so let's interpret some K values. On this top example, we can see we have a K value with 10 to the negative third. Remember, 10 to the negative third is a smaller number than 1. So this number would be 0.00465. So this isn't a super small number, it's just fairly small. So it means that at equilibrium, we're going to have slightly more reactants than we are products. So it is going to be a reactant-favored equilibrium. Now in this bottom example, we have 10 to the 12th, which is a very large number. This is going to tell us that at equilibrium, we're going to have way more products than we are reactants, so this reaction is going to be deemed product favored. All right, let's wrap up this lesson with an example. It says, according to the particle diagram shown, which is greater, the forward reaction or the reverse reaction? So remember, the forward reaction is going to be our reactants turning into products, and our reverse reaction is going to be products turning back into reactants. So let's look at our reactant molecules. starting with X. In time 1, we can see we have 3 X atoms, and in time 2, we have 1. So we are decreasing in reactants, which is telling us that we have a strong forward reaction because our reactants are turning into products. Now looking at Y2 on time 1, we have 1, 2, 3, 4 molecules. And on time 2, we have 3 molecules. So again, we are decreasing our amounts of reactants and turning them into products, which is telling us that we have a strong forward reaction. And then finally, with our product, XY, we are starting in time 1 with 1, 2, 3, 4 molecules, and in time 2, we have 6 molecules. So we're going from 4 to 6. And because we are increasing our products, that means that we have a very strong forward reaction. So all 3 of those is telling us that our forward reaction is greater than the reverse reaction between time 1 and time 2.